Chapter 30, sections 3 through 6. This is an overview of radioactive decay, which is one form of nuclear reaction, which is the main idea that you need to know about. Basically, due to the competition or disconnect between the Coulombic repulsion and strong attractive force that's holding the nuclei together, many nuclei are unstable. And this curve that I looked at in the previous podcast shows the curve of N versus Z for stable nuclei. There are plenty of unstable nuclei that either have too many neutrons or too many protons, or they're just too big. And these will decay to a more stable nucleus, and sometimes there's a series of decays before you reach a stable nucleus. But the main types of decay are as follows. There's alpha decay. And this is primarily, but not necessarily exclusively, big nucleides trying to get smaller. So when we look at this, coming back to this curve here, the elements along this part of the curve will spit out an alpha particle, which is a helium isotope, and make themselves smaller in the process, and the overall binding energy per nucleon will decrease. An example of that was given in the book. A fairly heavy nuclide, which is this radon isotope, will spontaneously fall apart into 88, that's radium, into 222.86 Rn, which is radon, plus an alpha particle, which is a helium-4 nuclide. Now you'll notice that the mass number, the total mass number on either side of the equation remains the same. 226 is 222 plus 4. That's an important conservation law, conservation of nucleons. The number of nucleons stays the same in any nuclear reaction. They get split between different isotopes, but the total stays the same. Similarly, conservation of charge must be observed as well, and so in this case the total number of protons remains the same. 88 equals 86 plus 2. And then there's beta decay. And this occurs when a nuclide has too many neutrons. So it tends to occur for lighter elements that are a little bit above this neutron number curve, although it can happen for heavier ones too. Example that's given: 14,6 carbon. Remember, for light elements, the number of neutrons and the number of protons tend to be equal for stable nuclides, whereas with this isotope of carbon there are 8 neutrons and only 6 protons. So this will decay, and basically it will gain a proton to try to redress the balance, and we end up with a nitrogen isotope that has 7 protons and 7 neutrons. So what's happened in this process is that inside the nucleus, a neutron has spontaneously converted into a proton to rebalance things. Now we have to conserve charge, so we're going to emit an electron, and that's the beta particle. Now this isn't an electron from the atomic orbitals, this has come out of the nucleus. A neutron has decayed, fallen apart into an electron, which flies off, and into a proton, which remains behind. This nucleus has gained a positive charge compared to this one, and we have to balance that by having an extra negative charge flying off. Now, in addition to the electron, we also get an anti-neutrino. This symbol here is the Greek letter nu, which signifies Nu, which signifies a neutrino. It's the Greek equivalent of the letter N, standing for neutrino, and the bar across the top signifies it's an antiparticle, an antineutrino. And the reason for this is that, as well as the number of nucleons having to be conserved, this nucleon number, mass number 14, we also need to conserve the number of so-called leptons, which are electrons, neutrinos, and other forms of subatomic particle. These are fundamentally different from protons and neutrons. And so if there's going to be, this guy has a lepton number of 1, and the antineutrino, because it's an antiparticle, has a lepton number of -1. 1 minus 1 is 0, so the total is 0 on this side, and it was on this side as well. So in beta decay we need the electron to come out to rebalance the protons and neutrons in the nucleus, and we need the antineutrino as well in order to balance the number of this type of fundamental particle, the lepton. There's also occasionally beta plus decay. Now this beta minus is when there's too many neutrons, and a neutron turns into a proton to rebalance things. Beta plus decay, there are too many protons. And this is less common, but for example, the example that's given in the text again is an isotope of neon. Now you'll notice this one has 9 neutrons, 10 protons, so it's a little below the line of stability here. It has too many protons. And as this curve suggests, it's usually more stable having an excess neutron rather than an excess proton. So this isotope is going to become more stable if it can lose a proton and gain a neutron. So inside the nucleus, a proton decays, so now we only have 9, and it becomes a neutron, so we maintain the same mass number. And in order to do this, we've lost a positive charge in the nucleus, so we must have emitted one, and we emit a positron. We saw that before with pair production. It's the antiparticle to an electron, and because this is an anti-electron, we're going to get a regular neutrino. So this has a lepton number of -1, this has a lepton number of +1. And there are a couple of other forms of decay. Electron capture, where an electron orbiting the atom is captured and converts a neutron to a proton. That's another way of gaining protons and losing neutrons. And then gamma decay is just the emission of electromagnetic radiation, oftentimes when a nuclear reaction takes place. The daughter nucleides on the right hand side of the equation can be in an excited state, which would be signified by an asterisk, and it relaxes to a less excited state by emitting electrons, emitting gamma rays, very high energy photons. This is exactly comparable to electrons, atoms emitting radiation when electrons move from one energy level to another. So nucleons inside a nucleus can exist in different energy levels, and transitions between those energy levels will cause emission of radiation. And because the energies are so much bigger, the frequencies of the light emitted are so much higher. So transitions between electron energy levels in atoms typically are X-rays or ultraviolet rays, but inside the nucleus we get much higher gamma energy gamma rays.